Thermoception, the sense of temperature. Our ability to sense temperature is what we call thermoception. In haptics, thermoception is of particular interest because it can be used to intensify perceptions of other variables of touch. For example, you can make a heavier object feel heavier by cooling it down. The weight hasn't changed, just your perception of the weight. So how do we perceive temperature? Temperature receptors are distributed throughout the skin, different areas having different densities of receptors. The hand, fingertips, as well as the face, especially the tongue and lips, have the highest density of these temperature receptors. Simply put, these are the areas of your body that are incredibly good at detecting varying temperatures. On the other hand, or should I say foot, the sole of the foot has the least receptors, and therefore not as good at sensing temperature. Let's go ahead and organize this information visually as sensory spots. You will notice the red warmth sensing spots are relatively rare, while we are absolutely covered in cold sensing spots. Because of this, you can detect changes in cold far faster and accurately than those in hot. If you think about it, it does make sense. In fact, most of the world around us is colder than we are. Now, to take this point further, the thresholds of detection for warmth receptors are twice those of cold. Now that's a big difference, isn't it? If we get down into the details, cold receptors have a resolution of roughly 0.02 to 0.07 degrees Celsius, which is more accurate than heat receptors, which range from 0.03 to 0.09 degrees Celsius. When we're talking about resolution, we mean what is the accuracy at which temperature change can be detected. These couple of tenths of a degree are the small changes your skin is sensitive enough to detect. But even this has its nuances. The thresholds further diminish if applied simultaneously at symmetric locations of your body. Anyway, all this doesn't take into account the actual speed of the temperature change. Lucky for you, faster extreme changes, what you would call dangerous, are detected far sooner than slow changes. But otherwise, a change of 5 degrees can go unnoticed as long as we keep it within what we call the neutral area. The neutral area is what we define as an area of temperature that is not detected as too cold or too hot. This is due to something we call adaptation, which happens anywhere between 17 and 40 degrees Celsius. But while I sit here and talk about hot and cold, you might have to ask, what is hot or cold? Try this. Take 3 bowls of water, cold, warm, and room temperature. If you have the patience, one hand in hot, the other in cold. Wait 5 minutes. Now touch the water at room temperature with the hand that was in cold water. Feels warm. And what about the hand that was in warm water? Feels cold, right? Why is this? This is what we call our physiological zero. This is our neutral or null point that is used as a reference. This is the point from where we determine what is hot or cold. As you've noticed in practice, it's a bit of a problem because our physiological zero is never actually the same. We adapt to our surrounding environment. What is cold in the sauna might be warm in the lake. But let's take this even further. We need to also consider spatial summation. The larger the area of the skin stimulated, the greater the magnitude of the response, further reducing our reaction time. That's the difference between testing the waters and diving right in. Despite all this range temperature gives us to understand the world around us, it lacks spatial recognition. That is, to pinpoint the where in temperature. Just be glad there's one exception: pain. You'll know right away exactly where an intense hot or cold pain is coming from. Now, we did say there are more senses of touch. It's not all about temperature. So up next, we're going to go through our sense of pressure, or what is known as mechanoreception.